Okay, so today I want to talk about derivatives of vector functions or parametric equations. Um, but it really depends on what you mean by derivatives. So in Calculus 1, you learned how to take derivatives and interpret it as a slope of a tangent line or interpret it as the rate of change at a particular moment. Those things kind of differ in this parametric or vector function setting. So let's take a look. Okay, so the derivative, when we think about the slope of the tangent line, is how much the y coordinate changes divided by how much the x coordinate changes. So to compute that, we need a formula like this. So this is the change in the y coordinate, and this is the change in x coordinate at a given time. And kind of if you squint your eyes, so I know the derivative is not actually a fraction, but if you kind of squint your eyes and kind of pretend you multiply dt and top and bottom, you could see that the dt might cancel out and you get dy over dx. So change in y divided by change in x. So that's what that's how you could compute a slope of a parametric function or a vector function. Okay. If you're thinking about the rate of change or how the particle is moving through space, then you wanna take the derivative and interpret it as a vector, right? So if you're at a particular point, you care about which direction are you changing and how fast you're moving at that moment. So the derivative makes more sense as a vector in that setting. So I try to kind of draw the two separate interpretation, right? So if you were looking at a circle of radius 5, and you're looking at a particular point 3, 4 on that circle, really what you care about is that slope when you're talking about slope of the tangent line. And let's see, if this point was 3, 4, and if you remember that tangent line is going to be perpendicular to the line to the center, then you can get the slope by looking at the, reciprocal, negative reciprocal of the slope to the line to the center. But if you were talking about a particular motion, then you might parameterize a curve going from the positive x-axis going counterclockwise, and then the derivative when the particle is at the point 3, 4 would be a different answer, right? So that would be the derivative, and 5 cosine happens to be x, so this should be 3, and then this should be a negative 4 at that point. So there's definitely a relationship between them. This vector is in that direction of the slope, but the interpretation is different. And the rate of change would change if it's going at a different speed and so on. Okay, if I'm talking about a slope, then maybe I want to talk about concavity of the curve itself as well. And there it's a little bit trickier than you might first imagine. You might think, well, if this is the formula for the slope, then you might think, well, the second derivative might be the second derivative in the y direction divided by second derivative in the x direction. But this doesn't quite work. So again, derivative is not a fraction, but if you kind of try to cancel it out, what you'd get is d squared y over d squared x, which is not the same thing. So what should you be doing? Well, you should be taking the slope interpretation derivative of the slope interpretation derivative, right? You're doing that twice. So once you compute the slope derivative of your parametric equation, then you plug that in, replace that with the new y, take the time derivative of it, and then divide the first time derivative of x. And then you'd get the dt will cancel out. You'll have d squared y over dx dx. So let's actually do an example. So this makes sense. Okay, so here's a parametric equation of some curve. You don't have to be able to graph this, but you should be able to say, when is this traveling in the direction that has a positive slope, and you should be able to compute whether at a particular time if it's concave up or concave down. Okay, so let's see how this will work out if we plug it in. So the slope is given by the derivative of y divided by derivative of x. So this is the y component of the parametric equation, and this is the x component. And then we take the derivative. So derivative of t is 1, and derivative of natural log of t is 1 over t. So this is the expression we get. I do hate fractions instead of fractions. So it does simplify. If you multiply top and bottom by t and multiply across, then we'll get t minus 1 on the top and t plus 1 on the bottom. Okay, so given a particular t value, so here the domain is positive t. So if t is positive, the denominator is always positive because it's positive number plus 1. The numerator depends on what the t value is. So it is decreasing, or the slope is negative when t is between 0 and 1, and the slope is positive when t is greater than 1, because that's what determines the sign in the numerator. Okay, all right, so that is the slope at a particular time, slope of the tangent line. And the concavity, what we do is we plug this formula that we just got into the top, and we take the time derivative of that. And then we divide by the first derivative of x, which we've actually already computed. So, okay, in the numerator, that's what we take the derivative of, and we'll use quotient rule for this. So the denominator times the derivative of the top is 1, minus the top times the derivative of the bottom is 1 over the square of the bottom. Okay. The derivative of the denominator we've already computed. That was the derivative of the x component. And again, we could simplify this. So I think if we simplify the numerator, the t will cancel out and you'll just have a 2. But again, trying to get rid of the fraction over fraction, if you multiply the top fraction with a t and bottom fraction by a t, you'll get t plus 1 on the bottom. And it'll just be 2 times t in the numerator. And this is a little bit hard to see. So we have a fraction divided by something, which is the same thing as multiplying this to the denominator. So you'll just have t plus 1 cubed in the denominator. Okay, and then here, um, as long as t is positive, the numerator is positive and the denominator is also positive. So it's concave up for any t greater than 0. Okay, so that's what the second derivative would be. Okay, and if I wanted to compute the velocity vector, the rate of change interpretation, you just take the derivative of each component with respect to t, component-wise, and then we're done. That's a little bit simpler, right? Okay, so I should add one more thing as long as we're talking about derivatives. Sometimes we don't really care about how the speed at which the particle is traveling. You care about which direction it's traveling. And then sometimes it's convenient to remove that speed. So you just look at the direction. So in that setting, what we might want to compute is what's called the unit tangent vector. So all we do is take the derivative velocity vector and divide by its speed. So we're just dividing by how fast it's going. So the direction doesn't change when we divide by a scalar. We always have a unit 1 magnitude vector that points in the same direction as the velocity. So that's what we'll end up computing later on. Okay, and maybe we could just do an example of this. So if we computed this as a velocity vector, then we also need to compute its magnitude. Okay, so let's see, in this setting, if we FOIL everything out, we'll get 1 squared plus 2 times the cross term plus 1 over t squared plus 1 squared minus 2 over t plus 1 over t squared. The cross term cancels out, and we'll get 2 plus 2 over t squared. Okay, and once we get the speed, the magnitude of the velocity vector, we take this vector and divide this by this amount. So the unit tangent is going to be 1 plus 1 over t over 2 plus 2 over t squared, and 1 minus 1 over t over square root of 2 plus 2 over t squared. Okay, and you know how I like to simplify these things. If I can avoid it, I don't want to write fractions instead of fractions because it's just painful to look at. So what we could do is we could do the same thing. We can multiply the numerator by t and also the denominator by t. But if I'm putting t outside of the square root and put it inside of the square root, that's like multiplying by t squared in the inside. So that will end up being t plus 1 in the numerator and square root of 2t squared plus 2 in the denominator, and very similar thing for the y component. Okay, which is still a complicated expression, but definitely simpler than before. Okay, all right, so we've discussed lots of different types of derivatives, and we have a lot of different vector arithmetic computation that we know how to do. The nice thing, I'm not going to go over this carefully, but the nice thing is that pretty much all the differentiation rules that you know and learn in Calc 1 or TMath 124 class is going to kind of carry over with a very similar formula. So we know how to add vectors. If you take the derivative of the sum of the vectors, it's going to be the derivative of the vectors and then added together later. Multiplying constant to the vector, you can pull the constant out if you're taking the derivative. If you're doing scalar functions, so this is a function, the regular function, one-dimensional function, times a vector function, then the product rule pretty much follow the way you expect. It's the same thing with the dot product and same thing with cross product. So product rule in all three different contexts work exactly the same way you expect. One thing you should watch out about the cross product though, because you can't change the order of multiplication, otherwise you actually change the resulting vector. So you take derivative one piece at a time, but make sure not to switch the order of these vector functions. Okay. And also chain rule also follows through. So that's kind of nice. And you might be thinking, why do we need to know these rules? Well, a lot of the understanding and formulating, finding formulas and in theory, it's very useful to know how these rules carry over into the new setting, so we can work those out. I am not going to prove all of these, but maybe just by example, show that it works for one of these rules. Okay, so let's say we're looking at a function 1 over t, and maybe I'll call the function u. Okay, so let's say I have both of these functions, and I'll compute the derivative two different ways and show that it's the same. So first, let me multiply them. So if I multiply 1 over t to each of the component, I reduce the power of t by 1 for each of those, and then take the derivative. So the derivative of this thing is going to be 0, 1, 2t. Okay, so that's one way to compute it. Let's also compute it this way. So if I compute the derivative of 1 over t is negative 1 over t squared, and derivative of u is going to be 1 comma 2t and 3t squared. Okay, so let's compute these two things. So f prime, which is this thing, times u is going to be so negative 1 over t, comma negative 1, comma negative t, all right, plus, now I want to multiply f of t times u prime. Okay, so what do I get? So 1 over t, comma 2, comma 3t. Okay, and if I added negative 1 over t and 1 over t cancels out to get 0. Negative 1 plus 2 is 1. And negative t plus 3t is going to be 2t. And now you see that it worked out to be the same. Again, this is not a proof. It's just showing by example that it works in this one particular case, but it does hold to be true for all of these other multiplications and composition. Okay, I think this is where I want to end the video now. I'll see you later.